Well, hello, good morning, good afternoon to everyone, and welcome to this session on geohazard risk assessment. My name is David Lopez. I'm a civil engineer from a Spanish engineering firm called INES, a company that has been working for the last 5 years in disaster risk assessment applied to transport infrastructure in the Himalayan region. With the support of Deshin Sharing and Masakatsu Takamutsu, disaster risk specialists from the World Bank in the region, we have organized this session in which 4 projects related with geohazard risk are presented. Before starting with the session, I would like to thank first of all the speakers for their participation and for making the session possible, as well as thanking you all, the attendees, as we are doing this session thinking on you. I would like also to add that at the end of the session, we will be having around 10 minutes more or less of questions and answers. So if you are willing to provide, ask any question, you can note it down in the chat and we will write it down, and we will give you the word once the different speakers have finished. Well, now I leave you with different speakers. We are going to start by Masakatsu Takamutsu, a disaster risk management specialist from the World Bank, as I mentioned before. He's a member of the South Asia Region Climate Change and Disaster Risk Management Unit. With a background in environmental engineering and water resource engineering at the World Bank, he's leading the South Asia Regional Geohazard Risk Management Technical Assistance Program and supports various water-related investment projects in the South Asia region. He's going to introduce you why is the World Bank financing this type of projects in the region. So I'm gonna leave you with him, and I hope you enjoy all of you of the session. Let me see.
Yep, thank you, David. And
it again. Sorry.
Yeah, the screen is coming. And the slide mode, please.
Very well.
Yep. Yeah. So thank you so much, David, for a kind introduction. So, as he said, like, so this session talks about the geohazard resilience in South Asia, especially for the Himalayan region. Then, if you could go to the next slide. And again, my name is Masatsugu Takamatsu, and I'm a specialist from the World Bank, South Asia Region Climate Change and Disaster Risk Management Unit. And thanks so much for those joining us today. Some are familiar faces on us, some are new, but thanks so much, and from everywhere or anywhere in the world. And next slide, please. So first, I want to a little bit of give you an introduction about the geohazard in South Asia. So as you know, the South Asia is home of the Hindu Kush Himalayas, and that is beautiful and gorgeous, and then it attracts a lot of people from all over the world, and then it actually a pride for those people, those who live there, and the countries there. But because of their challenging terrain, they pose lots of risks of landslide and geohazards. So especially in Himalayas, those geohazards can be triggered by both earthquakes and rainfall and floods, those climate-driven hazards. And also those rapid development in really challenging terrain is another factor to increase landslide disasters in South Asia. And then this picture is the Nepal landslide. Actually, this monsoon season, in Nepal, they had a lot of landslides this year, and also the North India as well. So so it is happening every year. And the next slide, please.
Sorry.
So the landslide, actually, it's really difficult hazards to manage. Why? Because it's very difficult to predict when and where a landslide occurs. And also it costs human lives and then destroy assets. And then the actual risk is increasing, I should say, because the more and more development, and also the climate change that is intensifying the rainfalls. And then those are the pictures from the Kerala, the landslides in 2018 monsoon seasons. So even not in Himalayas, those landslides are happening in South Asia, different regions as well. The next slide, please. So our approach to the landslide disaster risk management is threefold: risk mapping, risk-informed planning, and early warning. So first, risk mapping, it's because you want to know especially where the risks are, but then it requires high resolution data or up-to-date infrastructure or the exposure mappings. And then after those mapping, those risk-informed planning and policies are possible. For example, you may want to land use zoning to restrict development in hazard-prone areas, or infrastructure planning with known information of the risks, or the prioritize mitigation measures. And then also, but then even with those, you cannot mitigate all the risks. That's why early warning is becoming important, because with early warning, you can save people's lives. But then it also requires cross coordination and collaboration with hydromet agencies. The next slide, please. And so in South Asia, we are fortunate that because we use generous funding, and then we have a 5-year GFDRR Trust Fund program to strengthen regional geohazard resilience in South Asia. So we run workshops, studies, and trainings. Those give some opportunities for our counterparts and practitioners to exchange experiences, learning good practices, and then the new technologies. And next slide, please. So today we have 4 really successful showcases that was done in the Himalayan regions. Number 1 and number 4 studies are the risk assessment studies for the risk assessment and mitigation planning studies done in Bhutan and Nepal to the road asset. And then number 2 and number 3 are the satellite studies identifying the high risk slopes. And then that was verified in the field. So those, hope you will enjoy today's presentations. And I'll stop here and over to you. Thank you.
David, you are muted.
Thank you. So sorry. Thank you, Masa, for your presentation and introduction. The next speaker is my colleague, Marta Pertierra. She has developed her career within the civil engineering and environmental consultancy field, where she has specialized in risk-based asset management of transportation infrastructures. Marta counts with double master's degrees in civil engineering and in environmental sciences. She has been actively involved in the development of risk assessment methodologies to analyze the risk of infrastructures against natural hazards and the impacts that are derived from climate change, working as a consultant in several projects financed by the World Bank all around the globe. So now in this session, she's going to be presenting the geohazard risk management and resilient asset management system developed for Bhutan's Department of Roads. So Marta, please go ahead.
Thanks, David, for the presentation. Good morning to everyone. I am Marta Pertierra, and I'm going to be talking about the last project that we did in Bhutan in relation to geohazard risk assessment and resilient asset management. I'm gonna share my screen. So as I was saying, I'm going to present to you our last project in Bhutan, but also Bhutan's example in this path towards resilient road asset management. This project that I'm going to talk about took place between 2018 and 2019. It was funded by the World Bank, and it was developed for the Department of Roads in Bhutan under the Ministry of Works and Human Settlement. And the main objective of the project was the increase of resilience of the road network, the reduction of risks against natural hazards through the development of a decision-making tool. But we have been working with the Department of Roads of Bhutan for 5 years now. We started working in 2015 with them, where we developed a basic road asset management system, and we undertook the initial inspection of 2,000 kilometers in the country. After that, the following 3 years, the Department of Roads continued working themselves on the collection of road asset data that could fit that road asset management system. And then in 2018, INES came back again to the picture as we were awarded a project for the development of this geohazard risk assessment and the development of a tool, a system for the resilient road asset management. So we are helping here the Department of Roads of Bhutan to move from a reactive approach that was based on expenditure made after emergencies occurred to a preventive approach where the investment planning was based on the condition of assets, towards finally a risk-based approach where the strategy is based on the risks against natural hazards and in the future, hopefully, against climate change. And why is this important? In this graph here, you have the global profile of risks around the world from 2007 to 2020. The green boxes are environmental risks. If you see from 2007 to 2010, no environmental risks were identified across the globe. However, look on the right, 2020, almost every box is an environmental risk. And that is important not only in terms of the likelihood of the risk, but also their impact. You see there, climate action failure and extreme weather events are the highest risks that we face globally. The risk profile of Bhutan is not different. You see that it's a country that is highly exposed to floods, both river and urban flooding, and landslides. And that's not only in the present, but in the below graph there on the right of the screen, you can see the maximum rainfall for the last 10 years that has been constantly increasing. So these risks are not going to stop in the future, they are going to be worsened. That is important. And it has an impact on road maintenance. This data from the Department of Roads showed that on average, the expenditure on emergencies account for 40% of the road maintenance of the country, which is something that we want to change. We want to stop reacting at emergencies and start preventing, anticipating those failures, those risks. So we found that Bhutan was facing some challenges before the project. First of all, they were facing a challenge of lack of data in terms of inventory and condition of their assets, a lack of assessment methodologies to assess the vulnerability of their assets, the exposure against natural hazards, the risks, and a lack of prevention. They were reacting instead of anticipating. All that had a high impact both on road users because it created a lot of roadblocks, failures, accidents derived from that, but also a high rise in the road maintenance costs. So again, the objective of the project is to increase resilience of the road network by changing from a reactive approach to a risk-based preventive approach. And we are doing this with this project by the application of this methodology. First of all, in the project, we identified the areas that were prone to geohazard across the country. How? We generated hazard maps at country level. After that, we defined the theoretical framework for risk assessment. We also developed a GIS decision-making tool, and we applied both the framework and that tool for the assessment of a pilot case of 2,000 kilometers of roads. After that, we also designed mitigation and adaptation guidelines in order to increase resilience of the road network. We designed the standard operating procedures that different divisions of the road network should follow in order to increase the resilience of the road network. And we also provided capacity building at the end of the project. So the main outputs of the project are shown here. I'm going to go through them briefly in the following slides to explain them slightly. The first of them is, as I was saying, that theoretical framework for geohazard risk assessment. This was done, the risk is assessed by the combination of the likelihood of failure of the assets and the consequences that that failure has. And we have assessed that for two different scenarios. First of all, against the physical deterioration of the assets. This is going to help us plan repair interventions along the network. But we have also done the risk assessment against the occurrence of natural hazards. This is going to help us in order to plan adaptation and mitigation interventions. In both cases, the risk scoring is going to be to use this scale that you have there on the top right of the screen. You can see that it's an alphanumerical scale that is giving at the same time information on the likelihood and the consequences in a separate way. So by seeing the risk score, you can easily understand if the high risk is related to a high likelihood of failure or to high consequences of failure. And this risk has been calculated with some risk indexes that we have defined based on a series of parameters and real data of the assets. We have applied some algorithms to calculate each of these indexes that finally give us the risk scoring of the asset. We have done this in trying to leave subjective methodologies based on expert judgment and go for objective methodologies that are systematic and can be applied later in a repeatedly way so that they can be applied for other sections of roads or even other assets. Second output of the project, the hazard maps. We have generated hazard maps for flooding, seismic events, and landslides, and for different return periods, depending on the type of hazard, of course. We have also provided and generated risk maps. These have been provided for the different road assets, so pavements, bridges, culverts, earthworks, and also for different risk indexes. So not only for the risk of failure of the asset against natural hazard, but we have also provided the maps for the condition of assets, the coping capacity, the vulnerability, the criticality of assets. In this way, we are giving the information to stakeholders in such a way that inform their decision making. Other outputs that we generated, as I mentioned before, were the risk mitigation and adaptation guidance notes. These were potential interventions that could be done to reduce the vulnerability and increase the net resilience of the road network. These were divided by type of asset and also by the nature of the intervention, the repair, adaptation, and mitigation measures. We also provided standard operating procedures. As I was saying, they were roles and responsibilities that each division of the Department of Roads should have in order to jointly walk towards a resilient asset management. And finally, we provided capacity building on resilient asset management. This included several trainings along the 1.5 year duration of the project, and included not only the use of that decision tool that we developed, but also training on how to do field inspections, data collection, the standard operating procedures, the adaptation mitigation measures, and in general, how to achieve a resilient road asset management. So just to be finalizing, I don't want to bore you, I'm gonna highlight some benefits that the project had from our point of view. Both the framework and the tool developed allowed the Department of Roads to have an overview of the country's complete road network in terms of roads condition, exposure to hazards, vulnerability, or the risk of their assets. It also improved the data management as it made data easily accessible for relevant stakeholders. It also helped the Department of Roads in the prioritization of the interventions and support of the preparation of 5-year plans that the Department of Roads have to present to the Ministry of Finance. Also, it helps to define a resilient road asset management strategy. And of course, to reduce risks, increase the safety of the road network, and ensure that the long-lasting investments are achieved. Finally, I wanted to highlight some conclusions and some steps forward, because we have come a long way with the Department of Roads from the beginning towards a resilient road asset management, but we still have room for improvement, of course. In terms of conclusions, the framework and the tool that we developed are, first of all, scientifically rigorous because they are based on international standards and best practices. They are systematic, transparent, and repeatable, so they can be applied to other road sections and other key assets of the country and other countries. They allow an understanding of the transportation network as a whole, the condition in which assets are currently, their criticality risks, not only now, but in the future as well, against natural hazards and climate change. It supports the investment planning and also informs reporting required by not only the World Bank, by other multilateral organizations and donors. And it supports the increase of the network resilience and the reduction of risks. But as I was saying, we are not there yet completely. No? We still have some room for improvement. We still have to keep working. I'm finalizing.
Yeah.
Thanks. So just 4 things where we think that we should keep improving. First of all, we should calibrate and constantly improve the methodology with the new technology, with the register of events, that they have to keep having a register in order to calibrate the algorithms. It's also good to have an automatization of the data collection processes, both for the inspection of assets, but also for the monitoring of high-risk assets. My colleagues in the second and third presentation are going to talk about that. The institutionalization of the system, like developing a web-based system that allows the access to any stakeholder. And also, finally, very important, the inclusion of climate change considerations into the equation that currently have not been considered when analyzing the exposure and hazard modeling. Sorry if I go through over the 10 minutes. If you have, guys, any questions, give them in the chat and raise them at the end. I hope you enjoyed the other presentations. Thanks a lot for your attention.
Thank you, Marta, for your presentation. If you can stop sharing, please, 1 second. And in the meantime, I have now the pleasure of introducing you Thomas Omen, a professor in the Geological and Mining Engineering and Science Department and the director of the Computational Science and Engineering PhD program at the Michigan Technological University. Thomas teaches in the Engineering Geology course at Michigan Technical University. He has participated in over 8 million in research grants and published over 100 peer-reviewed publications. He's noted for his research in geohazard risk reduction, and beyond Michigan Tech, he serves as the editorial board member of the Geological Society of America and Association of Environmental and Engineering Geologists, joint publication Environmental and Engineering Geoscience, vice chair of the American Society of Civil Engineers, Geoinstitute Engineering Geology and Site Characterization Committee, a member of the AG Technical Committee on Landslides, and a member of the American Geophysical Union Natural Hazards Awards Committee. In this session, he will be presenting a project focused on proactive monitoring and assessment of critical slopes using remote sensing in the transport sector in South Asia. So please, Thomas.
Thank you, David, and I hope you're all able to hear me. And thank you, Martha, for that great presentation. So hello, everyone. As David introduced, I'm Thomas Omen from Michigan Tech University. My presentation is on how we can utilize proactive monitoring using remote sensing for monitoring landslides in South Asia, especially along transport sector and for regional scale studies. I will be demonstrating this study using examples from Bhutan. So traditionally, slopes that need monitoring are monitored using GPS, inclinometer, tilt meters. These methods are highly accurate and successful. However, they are costly and laborious to maintain when a large number of slopes have to be monitored, such as along road corridor, or when a regional scale monitoring has to be established. In such cases, installing and maintaining these traditional methods at several locations is challenging and not practical. Therefore, we need a method to monitor slopes proactively in uh, in transport sector or at regional scales. So let us look at what characteristics such a system should have. So such a system should have high spatial and high spatial resolution and large coverage. Should be able to make frequent and regular observations. Should have a global strategy so that we can cover any location on the globe, and should be reliable with 24/7 imaging capabilities for data acquisition. The good news that I want to share is that the modern spaceborne remote sensing meets most of these criteria. So let's actually take a look how we can use this modern spaceborne remote sensing for monitoring slopes. Here I am showing you two of the modern spaceborne sensors capable of Earth monitoring. One is an optical sensor, which is shown on the right, and the other is a radar sensor or image from a radar sensor. In this image, we see a location imaged using both the radar and the optical imagers at the same time. In the optical image, you can see that the cloud cover has masked several areas, whereas in the radar image, the cloud is not an issue. Similarly, the radar remote sensing has several other advantages, just like how we see in the terms of cloud cover. It can actually image past the cloud. The cloud is not an issue. There are similar advantages for the radar. It can operate day and night and does not rely on sunlight for imaging, so we can take images at any time. It's also all-weather imaging system. Besides, ground displacements obtained from travel path changes from the radar image can be measured at millimeter to centimeter scale, as the wavelengths of the radar signal is in centimeter scale. So this is a big advantage that the radar remote sensing provides. So in this case, for the Bhutan, we applied the radar remote sensing. So we had applied this technology to 3 different sites in South Asia, in India, in Nepal, and Bhutan. Due to time constraints for this presentation, I'll be just showing you the example from Bhutan. And the area that we analyzed is about 1,400 square kilometers. So pretty large area that we analyzed. And the road that area is, the road that goes through that area is the Ryotula road. And the largest city within that region is the Trongsa. We use the freely available Sentinel-1 images from the 2014 to 2017. This is available to the European Space Agency. It is available for anyone to download as free data set. On the left, we see results from the processing of the Sentinel-1 radar images. So let me explain what you're seeing here. The purple color represents point locations where we were able to make ground measurements using radar data. These total to around 190,000. These points are called the permanent scatter points, or in short form as PS points. Now these points are similar to an in situ observation using inclinometer or tiltmeter. So just imagine, in this 1,400 square kilometer, if you placed 190,000 inclinometers for 4 years, how much data you would get. That's the amount of data that we have got from these free satellite images from Sentinel. On the 190,000 PS points, we used a cluster analysis to identify points that have similar ground movement and high velocity. Because this is now a big data problem, because we have so much information from this area, we want to extract the most critical information. When we did this cluster analysis, we identified 45 such clusters in the 1,400 square kilometer. And those are the clusters that we show in the right image. I'll actually give you some more details on these clusters. Now, once we identified these clusters, we wanted to rank them. So we further ranked these 45 clusters based on the hazard and the risk exposure that they pose. So for hazard, we use the velocity and slope, with higher velocities and greater slope having increased weightage. And in the case of risk, we use the criteria whether these clusters are near houses or roads, with points on houses or roads having greater weightage. So based on these two, the hazard and the exposure, we ranked these 45 clusters into these using these ISO risk curves. And you can see here, now based on these ISO risk curves, it can be seen that the cluster 44 has the highest hazard and exposure, followed by 45, and then the 12. Now, let's actually take a closer look at this. So let me show you an example of what these points look like. So here, I have for you the cluster 45, which had the highest rank. And it is observed from the graph that between 2014 to 2017, 20 to 70 millimeter of slope movement has occurred at this site. These locations are near roads, and several points have movements close to 50 to 70 millimeter. Now let's look at one more case. Here I am showing you an example from cluster 12. We see that cluster 12 has a lot more PS points than cluster 45. Most of the points are on buildings, and the movements experienced by these slopes range from 20 to 80 millimeter during that time period. These two clusters show an example of how radar data can be processed using PSIn-SAR algorithm, and critical information can be extracted using cluster analysis. Now, when you do this approach at a regional scale, you can identify critical clusters and mitigate or monitor those slopes to reduce landslide risk. Because now you can actually identify which slopes you need to monitor, where you need to put your in situ instrumentation, or whether you need to mitigate. Those priority decisions can be made proactively rather than wait for a failure to happen, just like what Martha emphasized, taking advantage of proactive management. Here, after we did this study through a JICA project, there was a in situ measurement done. Here is an example of one of those locations that we identified near Riotola being monitored using field instrumentation. In the next presentation, Royota will be presenting more details of this study, so I don't want to actually take away from him. But I would like to just point out that as you observe from the tilt data, due to increased precipitation, a slope failure occurred at this site on July 8th. So these locations, when we identify using the radar remote sensing, they have great potential to be either monitored with the ground station or to be mitigated, because these are the critical locations within that region. Let me close with a few concluding points. It is evident from the study that radar-based slope monitoring shows great promise. The approach could be used to monitor the stability of current investments in transport sector, or it can be used for route planning for future investments. That's the big advantage of radar, because we have historic archive of radar data all the way from 1990. The availability of the historic archive of radar images allow for evaluating past record to see how stable the slopes in a particular area are. The continuous monitoring that this technology provides is valuable for early detection of ground instability problems and risk reduction. The early detection of instability issues can lead to significant cost saving for repair and better use of the resources, as emergency repairs are always costly and don't provide opportunities for proper planning. Combining the displacement measured from the radar data using PSIn-SAR with the slope and exposure information can help to rank the risk. Future hazard investigation and investment planning projects in developing countries should consider incorporating IN-SAR-based analysis. One of the limitations of the radar approach is that in highly vegetated areas, the IN-SAR-based monitoring can be a challenge due to significant temporal change. However, if there are roads or infrastructure in those areas, they act as good PS points and they provide good backscatter. Thank you for your thank you for listening, and I will be happy to answer your questions at the end.
Thank you, Thomas, for this interesting presentation. Now I give the word to the next speaker, which is Ryota Hasegawa, a consultant for the natural disaster management at Kokusai Kogyo, one of the leading companies of geospatial information technologies in Japan. He's specialized in geology, slope disaster survey, and countermeasure works. Currently, he's involved in slope disaster management projects in Asia and Central America. In this opportunity, he would like to introduce the project about the capacity development of the road slope countermeasures disasters in Bhutan. So go ahead, please, Ryota.
Hi, thank you for your introduction, Mr. David. My name is Ryota Hasegawa from Kokusai Kogyo in Japan. So today I will talk about road slope monitoring for ex-ante traffic control of high disaster risk road slopes in Bhutan, selected by using PSIn-SAR. So most of the country of Bhutan is in the Himalayas, in steep mountainous areas, and many slope disasters occur in the rainy season every year. This is a big problem for road traffic and people's lives in Bhutan. So to solve the problem, the Japan International Cooperation Agency, called the JICA, started a project for capacity development on countermeasures of slope disaster on roads in Bhutan in 2018. It will continue through 2022. The purpose is to improve the Department of Roads' capacity to implement effective slope disaster countermeasures along roadways. So our consultants conduct a Japanese technical transfer to Department of Roads, DOR. And our consultants share information with the World Bank to make Bhutan's slope disaster management better. So today I will talk mainly about one of the outputs in this project. Conditions of ex-ante traffic control are clarified, and discuss how we utilize information and data acquired from the World Bank. So first of all, I will explain what ex-ante traffic control is in this project. Ex-ante traffic control means blocking roads before road slope disasters occur. Here is a summary of the flow of the roadblock. In this project, we install an automated rain gauge at the site and send the data every 10 minutes to DOR headquarters. When the amount of rainfall exceeds the threshold, an alert is automatically issued and the road is blocked. For setting a threshold, we need disaster history and rainfall data. However, in Bhutan, there is no accurate record of disasters, so we also install the slope tilt sensor at the pilot site and monitor the mass movement and tilting or timing of slope failure. So today, I will focus on the methodology and the results of the slope monitoring. At first, we selected the target slope for monitoring. First of all, to narrow down high disaster risk road slopes in Bhutan, we conducted an identification of high-risk priority points from PSIn-SAR analysis provided by a World Bank project. In this figure, high-risk priority points are plotted on the map. And second, we conducted fieldwork evaluation of the high-risk priority points and defined slopes with a high potential of failure. And third, we conducted a prioritization of slopes in areas with high frequency of landslide occurrence recommended by DOR. And as a result, 8 potential target slopes were selected for conducting the slope monitoring. These places are written in red letter in the figure. Actually, almost all the slopes with a high potential for failure coincide with high risk priority points obtained from PSIn-SAR. So extraction of the high potential slopes by PSIn-SAR can be said to be high efficiency and the data is reliable. So from the 8 potential slopes, we selected 2 target slopes based on their suitability for monitoring equipment installation and function. One is Zonkarom and another one is Leotara, and both of the sites are located on the primary National Highway 4 in Bhutan. So we installed sensor at the height of 3 meters from the road and the 10-meter intervals to detect the slope failure. A total 10 sensors were installed at Zonkarom and 12 sensors at Leotara. And 1 rain gauge was installed at each site to conduct constant monitoring of rainfall and mass movement. So there are the results of monitoring data at the timing of mass movement and slope failure. So I will introduce 2 representative cases in Bhutan, in Leotara, sorry. And the top graph shows tilting angle versus date and time. The line chart shows the trend of the tilting angle of the slope tilt sensor. The bottom graph shows the 1-hour rainfall and the accumulated rainfall versus date and time. The line on the chart shows the trend of the accumulated rainfall. And the bars on the chart shows the 1-hour rainfall. The 1-hour rainfall indicates the amount of rainfall that occurred 1 hour immediately before the starting time. The accumulated rainfall indicates the total amount of rainfall from the time the rain began. If no rainfall has been observed for 12 consecutive hours, the accumulated rainfall is reset to 0 millimeter. So these results showed that before the occurrence of slope failure, the tilting angle gradually increased with rainfall and then resulted in slope failure. For example, on July 7th at 1:40, the accumulated rainfall exceeded 40 millimeter. Then the tilting angle also started increasing. And on July 7th at around 2020, 1-hour rainfall exceeded 20 millimeter. And accumulated rainfall rapidly increased. Then you can see that the tilting angle also rapidly increased. And 7 hours later, the signal from the sensor was cut off. We judged that the sensor stopped due to the slope failure. But the case of Leotara R4 also shows a similar trend. When accumulated rainfall increased at 1:40 on May 28th, slope tilting also changed. And at 18:40, accumulated rainfall rapidly increased. Then the velocity of mass movement increased. So multiple such cases have been confirmed at the Leotara site. So this graph is the plot of 1-hour rainfall and the accumulated rainfall at the timing of slope failure. Some Japanese highways set a threshold for ex-ante traffic control that combines the rainfall indexes of 1 hour rainfall and the accumulated rainfall. So this time we applied same indexes as in Japan. So in Deltara, we obtained a total of 4 cases which can be used for considering the rainfall threshold. However, when the point of sensor R4 collapsed, 1 hour rainfall was 0 millimeter. In addition, R8 and R9 also collapsed when 1 hour rainfall was 2.5 millimeter and 1.5 millimeter. From this data, it is thought that 1 hour rainfall seems not to be relevant for triggering slope failure in Deltara. So if we set the threshold, it becomes like this. In addition, continuous rainfall of 21 millimeter is not uncommon in Bhutan. And it is difficult to judge whether it is practically appropriate value. So our future work is collecting more data on slope tilt and rainfall, and considering other rainfall variables, and considering Bhutan unique situation. For example, characteristics of rainfall such as high frequency of short-term heavy rains and continuity of rainfall, and unregulated cut slope angle. So in the future, it will be necessary to set the threshold according to the situation in Bhutan while considering other various conditions. So to sum up, the major points of my presentation were PSIn-SAR is proving to be a very useful tool for the identification of high-risk slopes in mountainous areas. Multiple slope tilt sensors are successfully monitoring the mass movement and the timing of slope failure. And to set suitable rainfall thresholds for exam traffic control, it is necessary to continuously monitor and consider conditions. Thank you for your attention.
Thank you, Ryota. Thank you for the presentation. I'm sure that people were really interested. The last speaker now is Miguel Coulier, who has over 15 years experience in disaster risk management, climate change adaptation, resilient livelihoods, and institutional capacity strengthening. He holds a master's degree in international politics and another one in conflict and development studies. He has worked all around the Southern and Central Asia, conducting this type of studies. And in this session, he will be presenting a project of landslide risk assessment, risk mapping, and decision support system applied to the primary highways in Nepal. So please, Miguel, go ahead.
Thank you, David, and also thanks colleagues for this very interesting presentation. I'm very happy to follow this presentation. So my presentation is focused on a project implemented with support from the World Bank back in 2019. That is quite similar to the first presentation. So the aim was to assess climate and seismic risks for the road network in Nepal, analyze the criticality of these road sections from an economic trade point of view, identify hotspot areas where investment would need to be prioritized, and propose a suite of risk mitigation activities. So here on the slide, you see the extent, the scope of our geographical scope of our project. Mostly in Western Nepal, but also a very important trade route in near Kathmandu, where you see number 8. In terms of methodology, we started by conducting a spatial analysis of the road network, analyzing past disaster hazard experience, but also collecting data on climate change. Then we have done a prioritization of at-risk areas in these 700 kilometers of road through a multi-criteria analysis, a criticality analysis, and a hotspot identification. In a next step, we work closely with the Department of Road Engineers to define risk mitigation options and priorities for specific road corridors. And last but definitely not least, we developed a decision support system to allow DOR to continue the process and integrate the results of the other road network. We started our risk assessment by zoning the roads through a concept we call road corridors. So on the right side, you can see what a road corridor ended up looking like. So these are zones of influence, biophysical and non-biophysical influences that can impact the health of the road. We specifically also expanded that to catchments to see how drainage impacts roads. Our risk assessment combines a number of indices. 4 of them are focused on biophysical hazards. We have integrated climate change into these indices. And we added a 5th one per request of the government of Nepal, is to look at what is the pressure of connecting roads on the main network. So each of these indices contains a huge number of parameters, and in a similar modeling process, we've come up with scores for these parameters separately, but also for the indices as a whole, and applied a scoring system that goes from very low to very high. So I'll show you a couple of examples for one particular road. So this is, excuse me, this is a road in Western Nepal. So you can see we divided it in 1 kilometer sections. And on the left side, you can see the results of the rainfall-induced landslide risk index. And on the right side, the seismic-induced landslide risk index. We've done the same for flood risk and for drainage risk, as well as for biophysical pressures from intersecting roads, and especially on the right side, economic criticality. So we have risk maps available per parameter per index for all these roads. Then we have conducted a hotspot prioritization identification process, and this is a sample of the result. So the section in red are sections particularly high risk for this, in this case for seismic-induced landslides, but also high value in terms of demographics, population living there, trades, connecting routes, agriculture activity. So that's how these hotspots were selected through this iterative process. Another example you see for drainage, these are the red sections are the hotspots. Hotspots are particularly useful for the government to identify where they will prioritize their investment, but also where additional field surveys are required. As mentioned, our team has also worked on a decision support system. So the aim was to develop a very interactive decision dynamic system that is available online. So road engineers at the national level can use this to identify the risks and prioritize different sections of the road. I'm unable to present all the functionalities of our DSS, but this is a few examples. So users are able to select a particular road, they are able to select the different types of risks, and in a map viewer in the middle of the DSS, the results are pictured. So depending on what index and parameter is selected, the map viewer automatically updates this, and you can see it. You can see the results of the index. What is also included in this DSS is a number of layers, data layers on base maps. For example, a DEM, a digital elevation model, a past earthquakes, past landslides, geology, but also administrative information. For example, this is how the dam becomes overlaid on the risk index results. We have also, this is for geology, we have also integrated layers on climate change. So, for example, the annual mean precipitation can be overlaid on the different risk indexes. Importantly, we have a series of infrastructure layers, and the result is, for example, this, where the red points are schools and educational facilities, and the other layer is different roads. So each of these maps can be printed, so the Department of Roads can use this in meetings, can use this to go to the field, and can develop their own maps. There's also a functionality where you could click on a particular 1 kilometer section and compare the different results for the different indices. This is an example I'll show on the screen. And then we also have a function where you can download a whole risk profile for an entire road, which contains all the risk indexes. So when you click on this, you can see an entire profile, which the Department of Roads can also use in their decision-making processes. So this is a sort of concluding slide. The work there finishes. So in this, for risk assessment, this needs to be continuously reviewed and refreshed every 3 years. Indices need to be kept under review, and other indicators and parameters need to be added. A national level risk assessment such as this one needs to be complemented by field surveys, and the 2 previous presentations my colleagues have presented very well what should be done complementary to a national scale risk assessment. Other information can be added to the DSS, field survey photos, reports, drone imagery and videos. The DSS can also be used to develop zoning frameworks for each of the roads. And important to mention that this risk assessment is of course a priority setting tool, so it will help the Department of Roads to prioritize amongst their very large network what is required for anticipatory remediation. So this was my slide. I'm very happy to answer any questions, and thank you very much for listening.
Thank you very much, Miguel. Well, we have quite a few questions, but they are probably going to close down the session soon. So I am suggesting I'm providing my email address so you can forward me the different questions through email, and I will be forwarding them to the different speakers and answering you in the coming days. If you want, we can try solving some of the questions that I noted down here. We have a couple of questions for Ryota. One of them, I go ahead. What would be the role of the geology, soil types, clay combined with rainfall, whether hourly or accumulated? Were you able to cover the same?
Yes, thank you for your question. And actually, Zonkalom and Leotara is very, I guess, very similar geological type. And but actually, we have not so much data now, very less data. So, and we didn't get the characteristic of each site actually. So, yeah, but in the future, in this project, we are doing the geological survey, and in the future, we were planning to do the Zonkalom and the Leotara also. So, yeah. After getting the more data, we again consider the geological types and which geological types and the function of the and hourly rainfall, accumulated rainfall, all of the information again we have to consider. So sorry, anyway, we need to more considering in the future. Thank you.
Okay, thank you very much. Sorry that I think I forgot to write down my email, so here you have it.
David, I think it's well, it's the time now. I'm not sure if we should be closing the session and leave the questions for the emails. Yeah.
Yeah. Well, I think we have 4 or 5 more questions that I don't know if we have time to go ahead with them. So if you don't mind, please send them to the email that I wrote down here in the chat that you use for posing the questions, and we will get back to you. I would like to again thank you all for your participation, for your interest in the session, and we hope that you enjoyed. And well, hope to see more questions from your side, and we keep in touch. Anything that you can request from our side, please do not hesitate and contact us. I will be forwarding the different questions and requests to the rest of the speakers. Thank you very much to everyone. I don't know if Masa, you want to say anything, or we give for concluded the session.
Sure. Thanks so much, David, and thanks so much for the every audience and really nice presentations and really good questions. So thanks so much, and then thanks so much for David and Marta. It's your mid time, so now you can go home and sleep. So thanks so much for hosting, and thanks so much for everyone. So let me close the session. Thank you.
One last thing, Masa, I think that the session is going to be recorded or was recorded, and it's going to be available in the link in the forum. So if anyone can access it or want to access it afterwards, it's going to be there available.
Thank you for letting us know. Yeah.
Exactly. Well,
thanks everyone.
All. Thank you for your attention. We keep in touch.
Yep. Thank you.
Bye.
Thank you.
Bye.
Bye.
Bye. Enjoy the rest of the forum.
Yeah.
Bye.